There's a favorite movie of mine called Gunga Din. Old movie, somewhat racist, but a real great adventure movie. And there's this one scene in which the guru is in front of his acolytes, and he's talking about the signs that he has heard. He knows something has happened because a jackal growled on the left and was answered by another jackal. And these are the auguries, the signs. Well, there are some signs going on right now, and I thought I'd point out one to you. Rather remarkable thing here. This was in yesterday's Washington Post. It's an op-ed piece, in other words, it's sort of an editorial given to the newspaper that appears opposite the usual editorial page. In this case, it was written by Patrick Moore, who's one of the founders of Greenpeace. So a founder of Greenpeace, in the early 1970s, when I helped found Greenpeace, I believed that nuclear energy was synonymous with nuclear holocaust, as did most of my compatriots. They hadn't taken this course. That's the conviction that inspired Greenpeace's first voyage up the spectacular rocky northwest coast to protest the testing of U.S. hydrogen bombs in Alaska's Aleutian Islands. 30 years on, my views have changed, and the rest of the environmental movement needs to update its views too, because nuclear energy may just be the energy source that can save our planet from another possible disaster, catastrophic climate change. So this is something you all understand. You could fill in between the lines, right? Except, you know, he goes on and he refers, I'm not alone among seasoned environmental activists in changing my mind in the subject. British atmospheric scientist James Lovelock, father of the Gaia theory. That's the theory that the Earth is a living organism that takes care of itself. If the germs inside of it don't kill it, that's us. He believes that nuclear energy is the only way to avoid catastrophic climate change. Stuart Brand, founder of the Whole Earth Catalog. I remember when that came out, sort of teaching us how to live in an environmentally nice, benign way. Grow your own vegetables. He says the environmental movement must embrace nuclear energy to wean ourselves from fossil fuels. On occasion, such opinions have been met with excommunication from the anti-nuclear priesthood. A little bit extreme here in his use of language, I would say. The late Bishop Hugh Montefiore, founder and director of Friends of the Earth, was forced to resign after he wrote a pro-nuclear article. I just find it interesting. A year ago, there was an op-ed piece by a very liberal columnist for the New York Times entitled, "Nukes Are Green." So I don't know whether there's a change of tone here, whether people who are so frightened about global warming are recognizing that the poor countries who are going to be responsible for the CO2 increase, because they have no limits on them, even though they've ratified Kyoto, they have no limits, that these poor countries will produce an enormous amount of carbon dioxide, and we can't tell them to go solar because they can't afford it. I mean, we can, sort of. I can. I don't know if you can, but I can. But China can't. And we can say, let's do research. Okay, they are building one coal-burning power plant every week. And they're not going to wait for us to develop solar. So that's what's happening unless they go nuclear. So I find this an interesting development. It's reading the auguries when more and more people who strongly oppose nuclear are now saying it's the direction to go. Not everybody. Okay, those are digressions. Question? A comment. Go ahead.
Yeah, my comment is this, is that I just read the piece, I downloaded it from the Post, and he brings up the issue of nuclear fuel can be converted to make nuclear weapons. It's a serious issue. And then he goes on to say that machetes have been used to kill millions of people, so he puts it on the same line as like any weapon can be used to kill anyone. And what he's not saying is that nuclear weapons are the one weapon which could wipe out all life on the planet in 10 minutes. So this is still a serious issue.
Okay, of course, what you're saying is also full of mistakes and flaws, which I could now correct. You say it's the one weapon. It's far more dangerous than biological weapons. You agree to that. Okay, so I don't, this idea of reading some little section in this right now and immediately responding to it is not what I hoped to engender in the audience. I think what you should do is think of this as an issue to ponder and wonder about what's going on. And certainly do read the article, but I think a knee-jerk reaction saying he says this sentence here, which I disagree with for the following reasons when they turn out to be wrong, be more thoughtful is what I recommend. Seriously. You thought he was. Okay, good. Okay. Today we are beginning the first serious entry into a subject matter that you don't need to know. Relativity. I cannot honestly come up with any really good reason why a future president, future congressman, future Supreme Court member, future businessman or lawyer needs to know the theory of relativity. So forgive me for that, but I know a lot of you really want to know this stuff. So we're going to get into it in a serious way. You're going to really understand it. We'll have a couple of lectures on it, and you will understand it. You'll understand it as well as the physics major understands it. They may be able to do a few more things, like calculate what relativity will tell you about electromagnetic waves and how the polarization changes in different reference frames. They'll do things like that. They're not going to understand it better than you will. I assure you of that. The problems with relativity are not with the math. The math is not the heart of relativity. The math isn't even very hard. The essence of relativity has to do with the meaning of time. And what made it such a revolutionary breakthrough is that Einstein actually grappled with the meaning of time, was drawn to some conclusions that virtually everybody else would have rejected as absurd, and decided they couldn't be. They had to be right. He followed the consequences. One of those consequences turned out to be E equals mc squared, which we will be getting to. E equals mc squared, by the way, let me emphasize right at the beginning, had no role in the atomic bomb. The atomic bomb would have been built and used regardless of Einstein's work, although a lot of people think that E equals mc squared really accounts for the enormous energy in the atomic bomb. The fact is the enormous energy of fission was known independent of this equation. The fact that the energy comes from mass doesn't really matter. What you need to know is that you can have a sustained chain reaction that releases this energy. The enormous energy of nuclear explosions was known long before, of the explosion of the nucleus was known long before Einstein came up with his equation. So he was explaining something, but not necessarily doing anything that related to the atomic bomb. That's a fact that a lot of people continue to get wrong. So what is going on here? What is Einstein saying? He did his work based on previous conclusions done by some experimental scientists and also found lurking in Maxwell's equations. What they had discovered was that this is the famous Michelson-Morley experiment. Basically what they did is they looked at light coming from a distant star. And they could measure its speed. They were actually doing an interference experiment. But effectively, they were looking at the speed. As the Earth goes around the sun, you're first approaching this star, and then you're moving away from it. Now, when you're approaching something, the light's coming right at you, the velocity should be higher. And when you're on the other side of the sun, moving at 30 kilometers per second, that's pretty fast, faster than you can get in any laboratory. So their laboratory was the solar system. And as you are moving away, the velocity should be slower. And so this was a way to detect the Earth. If the velocities were that much faster and that much slower, then you'd know the Earth was basically at rest. That is, the sun was basically at rest. Anyway, actually, I'm not sure that's true. Depends on what they wanted to detect the ether. You know, here you have this strange material. What is waving when light waves wave? The vacuum, we now call it. It used to be called the ether. And are we moving through the ether or not? We should be able to detect the motion through the ether. If you're moving on a boat through ocean waves, the waves will hit you faster. If you're moving away from them, they'll hit you slower. Or maybe look like they're coming from the opposite direction if you really move. So want to detect the ether. This was the Michelson-Morley experiment. It came up with a very disconcerting result. When the Earth is moving towards the star or away from the star, the speed of light was exactly the same. Lorentz had come up with a possible explanation for this. He said when you're moving towards the Earth, you are compressing the ether. And when you're moving away from the star, rather, not the Earth, the star, you're stretching it out. And this could have, what it could do is affect your measuring instrument. So you're moving towards it, but the change in the shape of your rod will be enough to just make you think the velocity isn't changing. You know, you have to measure a distance and a time. So he came up with this thing. He said things contract when they're moving through the ether. The ether being this stuff like the water is to water waves. The ether, this was a name they gave to the thing that carried the light waves. He came up with something called the Lorentz contraction. And he said it will get shorter by the following factor. If you're moving at a velocity v, and the speed of light, we'll call by convention c, this is your velocity. Then when you move through the ether, you get squeezed, and there's a factor which we now call gamma. It looks like a little fish swimming straight down. Gamma is 1 over the square root of 1 minus v squared over c squared. This is his equation. And then he said this is how much it'll squeeze. And if v is fairly small, you hardly notice it. This thing will be, you know, maybe a few atomic sizes. This squeeze down factor. It's called the Lorentz factor. It was Lorentz who came up with it. This whole thing is called the Lorentz contraction. And let me give you a little more nomenclature, too, because this might actually help. I'm going to make up a new term, but it's not a new term. It's a term out of science fiction. We can measure our speed. Right now, I'm going about 1 mile an hour. But I can measure it as a fraction of the speed of light. So right now, I am going, you know, I have to work out the number, a tiny fraction of light speed. Light speed is when you're going the speed of light. Suppose you're going half the speed of light. Then you're going half light speed. In science fiction, they talk about going 10 light speed, 10 times the speed of light. Sometimes they talk about warping space and going the equivalent of light speed. So I'm going to call the light speed beta. This is a term that's actually used. It's a B with a little tail on the end of it. It's a Greek letter. Beta will be what we call the light speed. And what it is your velocity divided by c. So if you're going half the speed of light, your light speed is 1/2. And then I could write this Lorentz equation in the following way. Gamma is equal to 1 over the square root of 1 minus beta squared. So that's how the light speed comes in. We're going to be seeing this. And this is the one equation that we need to understand relativity. This is the heart of it. This one Lorentz factor will be the key thing to know. So it's going to be more interesting than it looks right now. So here was the conundrum. Einstein had to figure out some way to make more rational sense of this. And instead of Lorentz contractions and things like that, he came up with he asked himself, what in my understanding of reality could change that would make the speed of light actually be the same regardless of how I'm moving? And he came up with a theory of relativity, the one self-consistent way to make this all happen. To do that, The only thing he had to give up, no complicated math, he only had to give up was our understanding of the nature of time. That's what relativity is all about. It's the understanding of the nature of time. And his most striking conclusion, I will illustrate now with a slightly exaggerated example. I don't have a good demo. So I want you to pretend along with me that I'm taking the speed of light, and instead of it being 186,000 miles per second, basically a distance to the moon, almost, in 1 second, instead of it being that fast, let's assume the speed of light is really about 5 miles per hour. And then if we just have that conceit, that idea, then I can really do things in the lab that will illustrate what happens. So, for example, let's look at our watches. Well, you can think watch, and I'm going to start counting seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? What I've just illustrated to you is what's called time dilation. You and I are now looking at our watches, and your watches are about 5 seconds faster than mine. I'm assuming they were synchronized when we started. You have experienced more time than I have. Why? Because I was moving. If that bothers you, then it means you've been paying attention. This is the effect of time dilation. Time dilation means that if you have two things happening together, but one object has been moving, it has actually experienced less time. If that sounds crazy, I really ask you, why does that sound so crazy? Isn't that your daily experience? Isn't that something you're accustomed to and used to? If you are doing something you enjoy, doesn't time seem to go real fast? What does it mean time goes fast? Fast compared to what? Well, compared to someone else's sense of the time. If you're waiting for something that you're really looking forward to, the time seems to go slow. This is an everyday experience. Einstein used to give these examples, not because time really slowed down that much in relativity theory, but only to say, hey, you shouldn't be so surprised at this. The surprising thing isn't that time slows down, it's that it usually doesn't. The surprising thing is you can all have watches, and at the end of the day, if you have a decent watch, they'll all still have the same time on them. Isn't that surprising? You learn that. Most parts of the world, the people who don't have watches would not even realize that. Never occur to them the exact same amount of time passed. But you got to be here on time. If you're not here on time, you may miss a quiz. So you learn. You're here because you have learned. You have to learn that stuff. You have to learn how to meet schedules and so on to come to Berkeley. Much of the world, that's not so important. But in our society, it is very important. Yet it's not obvious. I think we are trained by our parents. I want you to be here when your watch says such and such a time, and your watch is the same thing as mine. There's no excuse that your watch stops. You should have gotten a new battery or something like that. But it turns out now that what you were taught is all wrong. Not completely wrong. It's still fairly accurate. But a moving object does experience less time. How much less? By a factor gamma. You want to know how much time slows down? Plug it in. Put it into your calculator. I have some numbers here that I worked out. Suppose you're going half of light speed. Okay, so beta is 0.5. 0.5 squared is 0.25. 1 minus 0.25 is 0.75. Take the square root of that and 1 over that, and you get gamma, and it's 1.15. So Beta, half of light speed, 0.5. Gamma, the time slowdown factor is 1.15. You slow down by 15% if you're going half light speed. That's not very much for going so fast. None of us have ever gone that fast. And if we went that fast with someone else, they'd slow down too, so wouldn't really notice it. Amazing that you won't notice it if you're traveling together. And we're going fairly fast around the sun right now. We're going 30 kilometers per second around the sun. That slows us down a little bit. Let me give some more, but it's such a small number. Suppose we take, let's take 30 kilometers per second. That's our V. C is 3 times 10 to the 8th meters per second, which is 3 times 10 to the 5th kilometers per second. So that's 300,000 versus 30. So let's say what beta is. Beta is 30 kilometers per second divided by 300,000. That's 1 in 10,000, 10 to the minus 4. Beta squared is 10 to the minus 8. 1 minus beta squared is 0.999999989. Square root of that, well, let's see, I have a little shortcut here. Gamma with 8 nines, I worked out that gamma would be about 0.7 times 10 to the, let's see. No, let me do this another way. I didn't work this out beforehand. The square root of 1 minus beta squared. For those of you who have studied calculus, you'll know that for such a small beta, this is approximately 1 minus beta squared over 2. Needless to say, I will not ask you for this kind of stuff, which is 1 minus 1 over 1 half 10 to the minus 8. 1 over that, which is gamma, is approximately 1 plus 1 half times 10 to the minus 8, which means it's 1.00000000000, and out here in the ninth decimal place, it's 5. So, because we're going around the sun at this big speed, our time is slowed down by this much compared to the sun time. Very small effect, very hard to notice. Einstein predicted that this would happen if you got up near light speed. So do we ever get things up to near light speed? These days we do. I did it when I was a graduate student. And I continue doing it as a researcher. I take radioactive nuclei and get them going at 90% the speed of light. Do this in the lab all the time. It's called a particle accelerator. You want to get them up to high energy. And even now, if you were a physics major, you could take a laboratory, a junior lab, in which you work with radioactive particles going at near the speed of light. In one of the labs, you actually measure how much time is slowed down. How do you know time is slowing down? Because the particles don't decay so fast. Their lifetime is increased by exactly this factor, the Lorentz factor. Their time slows down because they're moving. This leads to certain paradoxes. Suppose you have two twins. And I like to imagine that one becomes an astronaut, the other becomes a physics professor. The astronaut goes off in some super modern rocket that we don't have yet, at 99% the speed of light. And at 99% the speed of light, I did work out that number, the Lorentz factor gamma, let me put this over here, you can work it out too. It just takes a calculator. And there's the equation. And that equation, I'm not going to ask you to memorize that equation, but you could write it down and plug it in. It's not that hard to do. And if you do that, at 99% the speed of light, so beta equals 0.99, the light speed of 0.99. Then you get gamma is equal to 7.1. 7.1, that means time slows down by a factor of 7. So my twin going off to Alpha Centauri, taking, let's say, I don't know, she's not there after 7 months, but 7 months later, I will be 7 months older, and my twin will be 1 month older. At that point, twin decides to come back, same speed, we get back together, and I am 14 months older, and the twin is 2 months older. Now, this may not seem like a lot when you're my age, but if they're babies, it's a big difference between a year, 2 months. The person who was traveling actually experienced less time. This is called the twin effect. And it's simply time dilation, the twin effect. Sometimes it's used to make relativity sound absurd. There's also something called the twin paradox. So let me now, I've told you what the twin effect is, let me tell you what the twin paradox is. If you look up the twin paradox, you will see 10,000 web pages on the twin paradox, each offering their own explanation, some of them using it to show that relativity makes no sense. So the twin paradox is different from the twin effect. The twin effect is what I just said. The twin who went out and came back is now younger. The twin paradox is the following. Who's to say who was moving? Right? I mean, hey, from the point of view of the astronaut wasn't moving. It was Muller who was moving. That's ignoring the fact that the twin might have the same last name, but Muller, he went away and came back. So Muller should be younger than me, but wait a minute, I'm younger than him. Oh, there's something wrong here. That's logically contradictory. Who's to say who was moving? That's called the twin paradox. And it's based on a misunderstanding of relativity. Some people say the theory of relativity, basically Einstein showed all motion is relative. And because of that, who's to say who's moving, right? Well, Einstein was well aware of this paradox, and he explained it to everybody who would listen, but still a lot of people don't listen. Einstein did say all motion is relative, but not all acceleration is relative. If you are moving, and then you change your direction, then the calculations become more complicated. I could do them. I did them. I've published articles showing how you do them. It's not really that hard. But the twin, only one twin actually turned around. Only one twin felt the acceleration, felt the force, and actually turned around. We are not completely equivalent. I did not fire, the physics professor who never leaves home, except right after class, did not fire my rockets and turn around and change my velocity by such a large amount. So there is no equivalence there. Now, in fact, one can do the calculation, it turns out, from the point of view of the astronaut twin. If you take into account the effect of acceleration, then you will find from doing the calculations, I did this in an article published 30 years ago, show that the astronaut twin will indeed be younger, even from the astronaut's point of view. It does work out, it's just the equations are a little bit more complicated, because the acceleration makes them complicated. The neat thing is, if you do all of your calculations from one frame of reference, like this lab here, then the calculations are really simple. Everything else slows down by this factor. For those of you who don't like putting square roots into calculators, I have a table here. I've done it for you, just to get a sense of what it's like. This is in the book. So here's light speed, and here's the Lorentz factor. It's the same equation he had. Lorentz came up with this first, but he was using it for a Lorentz contraction to explain the Michelson-Morley experiment. Turns out to be just the factor that Einstein then derived for time dilation. So here it is. If you're moving at 0, well, the Lorentz factor is 1. Basically, you don't change. Time goes at your rate times 1. It's the same. If you're going 1/4 the speed of light, then the factor is 1.03. Time slows down by 3%. It's enough to be measurable, easily measurable. In fact, the time effect has actually been measured in airplanes, in jet airplanes, traveling around the Earth. They put in clocks and compared them to clocks on the ground. They brought them back, and indeed, the airplane changed by just the amount calculated. So this has been done at airplanes. It's hard to do at lower speeds, but at 1/4 the speed of light, it's still only 3%. You might not notice that if you weren't paying attention. I mentioned already that at half the speed of light, it's 15%, 1.15. Here's a neat thing for those, some people here actually enjoy playing with math. If V over C is 3/5, then this number turns out to be exactly 5/3. The square roots work out. They also work out if this is 5/13. Some of you may start noticing right triangle things here, and you might want to look at that. This one becomes 13/5. Oh, I'm sorry. No, I made a mistake here. This one was, I put in the wrong numbers here. I was copying the wrong column. So let me correct these here. Okay. It's because these things form 3, 4, 5 right triangles. If this one is 3/5, then this number turns out to be 5/4. And if this number turns out to be 12/13, the speed of light, that's getting pretty fast, then this thing becomes 13/5, which is more than a factor of 2. I mentioned already that at 99% the speed of light, this turns out to be about a factor of 7.1, not exactly. And at 0.99999, the speed of light, you can do this on your pocket calculators, you get that the time factor is 224. So if you send a particle going that fast, a radioactive particle, its half-life is increased by a factor of over 200. This is a big effect. It's such a big effect that it would have been discovered even if Einstein hadn't predicted it. It would have been seen almost within a few years in radioactive particles. It couldn't have been missed. To me, it's one of the most amazing events in theoretical physics that based on some measurements about how the speed of light as the Earth is going around the sun, Einstein said the only really proper way to handle this must be to change what we know by our meaning of time. Time must be slowing down by Lorentz's factor. And then based on that, made these predictions that turned out a few years later to be precisely correct. We need to put these things in our GPS satellites because the GPS satellites have clocks. And they're going around faster than an airplane. They go around 24,000 miles in an hour and a half. And so the GPS satellites have to take this into account because if they wind up losing a fraction of a second, they will send a signal to us. Their clock will be wrong. We'll have the wrong position. So the GPS satellites have to take this into account. Now, you don't really need to know that as a future president, except someday you're going to be, having dinner at the White House with some executive from a satellite company, and you'll say, the GPS has really been a wonderful thing for us. Of course, it was put up by the military, but now France is putting up one, Europe is putting up one, and it's kind of neat that you guys have to take into account special relativity to get it accurate enough. And they'll go, oh, right, yes. Of course, thank you. And they'll check with their engineers to see if they really do take special relativity into account. And they need to. Now, what does this do to our reality? It turns out there are some other effects that Einstein had to include. The original Lorentz contraction was part of his theory. That an object, when it is moving, let me demonstrate this, because I'm going to put up here something which is about 2 feet long. And well, this is more like 3 feet. No, I'm not going to do it with that. I'll do it with my hands. It'll work better in my demo. So here is an object, and now I'm going to start moving. Okay, so here I go. And that's about 2 feet long. Okay, as you all can see. Let me go back this way. Notice it's about 2 feet long. You can measure it. 1, 2, 3, 4, 5, measure all the inches. 24 inches? Yeah, so it was 2 feet long, still is. Now, one of the things you may have noticed is that measured with respect to the laboratory, it wasn't 2 feet long. It looked like it was about 3 inches long. Measured with respect to my moving ruler, which was also rather short. You thought my ruler was kind of short. I mean, here's my ruler, and as I'm moving, you look at this ruler, and it seems awfully short. But when I use that ruler to measure this thing, I find it's still 2 feet long. What I'm saying is that the length of an object depends on the reference that you're using to measure it. If the reference is a moving reference or a stationary reference, you may get a different length. In fact, you will, according to relativity theory, the object will be shorter by just the factor Lorentz said. That's in addition to the time dilation. The factor will get shorter, like by this factor. The factor is exactly the same. If I'm moving at 5/9, the speed of light, it's a factor of 200 times shorter. It's called the Lorentz contraction. Doesn't that squish the object till it breaks? Well, no, because you see each atom is squished too. The atoms become disks. They're not round anymore. I mean, in your frame of reference, they're disks. In my frame of reference, they're round. How can that be? Well, it is. Why not? Did you ever look at an atom? No, right? You've seen me drawing them, but what's so bothersome about that? It means your sense of reality depends on the reference frame? Yeah. Does that bother you? Why? Here we have just covered the 2 key features of relativity theory. Actually, a little bit more than that. Because what I'm saying is time slows down. But my clock, you look at my clock and you say it's going slow. I look at my clock and say it looks about right to me. And then I compare it with your clock and I find that mine is, yours seems to be ahead of mine. That as I'm moving, I get squished. But I don't sense a squishing because the atoms are squished. I don't feel anything any different. When you look at me, you say, why does he look like a pancake? But I don't feel like a pancake. Everything still works. Sometimes people wonder, well, the time dilation. Maybe what's going on is that time isn't slowing down. The clock is slowing down. Right? And my heart rate is slowing down. And everything I could possibly imagine is slowing down. And yeah, that's an alternative interpretation. But isn't that what we mean when we say time is slowing down? They're indistinguishable in my mind. Saying time slows down is just a way of cutting through additional questions of what about radioactive atoms? Well, if it's time that's slowing down, then you make predictions that radioactive atoms would slow down too. In fact, you make a prediction that you won't be able to find anything that didn't slow down. And so far, that prediction has been 100% verified. So using as your paradigm the idea that time is slowing down has been enormously predictive. And in physics, that's what we do. That's what we call a good theory, is one that makes predictions. So this is one of the best theories we have, that time is slowed down by exactly that factor. I did work out a number here for an airplane. Suppose V is equal to 675 miles per hour. That's about what I'll be flying in a couple hours at that speed. That means that the light speed factor, beta, is 5 times 10 to the minus 13. Does that seem right? And that means if you work it out, you will lose. The factor here is very small, but I have to check this calculation because I have this out of context here, that you'll lose just a few billionths of a second every day by traveling in an airplane 24 hours a day, you would lose just 44 billionths of a second in time every day. Do you lose it? Well, you don't really lose it. You experience less, but it's not lost. You'll live longer. The astronaut who's aging so slowly will outlive the person at home. That person's lifetime is based on the biology and how long that biology can continue to function at that kind of a rate. And if they're experiencing less time, they will just outlive. If you want to see the future, all you got to do, you don't want to freeze yourself. You could do that. That's not as clearly going to work. But you take a trip at this speed here, 99.999 light speed, light speed, 0.99999 light speed. Your time will be slowed down by 224. Spend half a year traveling out and half a year coming back at those speeds. You arrive here, you will have experienced only a year. You will only be 1 year older, only 1 year wiser, or whatever comes with that 1 year. And Earth will have progressed 224 years. So the Earth, you will be seeing the future. Of course, you will be stuck in the future, too. There's no going back at that point. So you can, you will all see the future tomorrow. But that's not what people usually refer to. Now, let me say a few things about the way this subject is sometimes taught. Because, what I've said is not, it's not implausible. It's not completely absurd. It's such a small effect that it's not surprising you didn't notice. But it doesn't really sound that mysterious, really. Is this what relativity is all about? What about the fourth dimension? What about all that kind of stuff? So let me cover that stuff now and tell you how you can make this stuff seem much more mysterious than it really is. So here's the way it is typically done. We start by saying time is the fourth dimension. Mystified? The purpose was to mystify you. Time is the fourth. What does that mean, it's the fourth dimension? It turns out it means essentially nothing. It is a definition of dimension in a technical mathematical sense. So let me just describe the math to you so you'll know where this is coming from. Normally, when we specify a position, you can specify it based on some coordinate system. You can say this position is the surface of the Earth at latitude x and latitude y. You could say it's an altitude, latitude, and longitude. 3 numbers specify a position, and that is true. Sometimes we will put up x, y, z coordinate system, and you say every position is specified by x, y, and z value, and that's the position. Once you know the coordinate system, you specify it with 3 numbers. When you can do that, we say you live in a 3-dimensional world, x, y, and z. You can be at x and y, and the same x and y are different z. Those are different locations. We say there are 3 dimensions, x, y, and z, or latitude, longitude, and altitude. These are just different coordinate systems. So we live in a 3-dimensional world, a 3D world. You need 3 numbers to specify a position. Now, when Einstein worked out his mathematics, he realized that specifying position wasn't enough. He wanted to include time in. So he came up with the idea of so this is for 3 dimensions, specify a location. By the way, that's still true in relativity theory. Really still true. Now, suppose instead you want to include time in, then we will say instead of a location, let's specify an event. What's an event? Well, that's a location with a time. Here's an event. Ready? The event will be Muller clapping his hands. It took place at a certain location, x, y, z. There it is. And it had a certain time associated with it. So we have to specify x, y, z, and also the time. And if we specify 4 things, then we can refer to the event. We can give it a name, Muller clapping its hand. We can say, your birthday party last year. Now, your birthday is a time, but your birthday party is an event. It took place at a certain place, a little bit of an extended time maybe. So let's talk about the blowing out of the candles. That was an event. And that just means it had a location and a time. Once you've located it and specified the time, it's unambiguous. The blowing out of the candles is what took place at that time. This is the concept of an event. Now, if you want to specify not locations, but events, you need 4 numbers. And so by the technical mathematical definition of what happens when you specify 4 dimensions, you say this is 4 dimensions. And time is the 4th dimension. Now, people who don't understand this or who want to impress you will try to make you think that time is like the other dimensions, right? You can move this way, and you can move that way, and you can move that way, and you can move forward in time. But I can also move that way, and I can move that way, and I can move backwards, and all those. Try moving backwards in time. It's not so easy. So time really is different from the others. I mean, I happen to be here. We happen to be now. The here is fairly definite. It doesn't change very much. But if I use the word now a second time, as I just did, it's not referring to the same time. It's referring to a later time. And if I said now again, that's a third time. Every time I use the word now, it means something different. It's a different time on my clock. Every time I use the word now is different from now. It's really weird what time does. This progression of time is really strange. It's interesting to see what physics says about the progression of time. The answer is almost nothing. The progression of time is something we really don't understand well. Some people try to explain it in terms of entropy, but a lot of that is just putting more complicated things into the fact that we don't really understand it. To call it the 4th dimension, technically it's the 4th dimension, if what you need to specify is an event instead of a location. To say it's, sententiously say, it's the 4th dimension, can really cause a lot of people to say, oh, I don't understand relativity theory. It's not that. Now, it turns out, of course, when you are moving, your location and the fact that you are moving affects the progress of time. And so the dimensions affect each other in this way. And there is a consequence of the fact that I'm moving on my time, and also in my space. My rulers, which don't look very short to me, look remarkably short to you. There's no additional force needed to squeeze this thing in. It just gets short because all the atoms get short. This has been measured too. You can see this in atoms because if you take large nuclei and bang them together at slow velocities, you can see the interaction that takes place by the way they come out. If you do it at very high velocities, the interaction is exactly what you get from pancakes banging into each other. Lorentz contraction is, again, something that is very well measured. And the same effect, the same number comes in both. The Lorentz contraction is reduced by the Lorentz factor and the time dilation by the gamma factor. Now, let me talk a little bit more about the Lorentz factor because there's one other thing that is lost when we're discussing time, which is a consequence of this, and that's the following. This is something that maybe you'll find even more disturbing, and actually, in my mind, has implications for philosophy, not just physics. Philosophers like to learn about relativity theory because it does address. We don't understand time in physics, we really don't. But we know some things about it, we have made some discoveries about it that are true in the world that are surprising. And so that's what you need to know. But now let me do the following. Let me measure the length of a moving object. And suppose this happened to be passing by, and I want to measure the length. I can measure the position here, and I can measure the position at the end. Oh my God, they're at the same position. Does this thing have zero length? No, Muller, you did a dumb thing. You got to measure them at the same time. Oh, of course. We measure them, boom, okay. Thing goes by. That's the length. The difference in positions, that distance, that's the length of an object. Einstein, in his first paper in relativity, gave these really dumb examples because he was talking to the most sophisticated physicists in the world, but he had to point out things like, well, if you're going to measure something, you got to measure both ends at the same time. He had to do that because in relativity theory, measuring things at the same time when clocks are running at different speeds is not such an obvious thing how to do that. Let me demonstrate this, because using these numbers and so on, you can now work out the math. And what I'm going to do is put my hands down on the table at the same time. You ready? Okay? Now, some of you over there may think I put down this one first. That's because the sound reached you from that one before it reached this one. It's because it's a little bit closer, but you know it's closer, so you know how to compensate for that. So you know they hit the same time. Even though the sounds didn't come at the same time, you know they hit at the same time. We're not talking about perception. We're talking about reality. So if I do this, and you know this one's closer, you'll say, well, they happened at the same time if the sound from this one came first by a little bit. So this has nothing to do with perception. If you see it hit a little bit sooner, you'll say, yeah, but it's closer. So light got to you a little bit faster. But you know how to take that into account. When you take that into account, you find they hit at the same time. Now, I'm going to, again, turn down the speed of light to just a few miles per hour. And I'm going to do these simultaneously. Right? They were simultaneous. Now with the slow light, I'm going to start moving. And again, I'm going to do it simultaneously. Okay, so now what I'm going to start doing is talking as really fast, because when I start moving, I will be going slow. And now let me move these down simultaneously. Okay. This comes out of these equations. I'm not going to derive it for you. Typically, we do this in the physics major class. But two events, event 1, event 2, position and time, they have the same time in this frame, the frame of reference of the table. When the frame of reference moving with me, they would have different times. If I make them have the same time in my reference frame, so I do them simultaneously, simultaneously, they won't be simultaneous for you. We lose the concept of simultaneity because of the time transformation and the space transformation. Put them together, and you lose simultaneity. What does that mean? Well, in some cases, if I say it's simultaneous, reference to my reference frame, in your reference frame it won't be. Of course, you could always calculate what it'll be in my reference frame, and maybe you could say this, well, is it simultaneous? Well, not in my reference frame, but it is in Muller's. And that would be the right answer. The answer depends on the frame of reference. Is that really bothersome? Does that really make your mind hurt? That even the issue of simultaneity depends on the frame of reference? Well, think of the following. If I asked you, what is your velocity right now? And just write down one answer, pop quiz, right? One answer, put down your velocity, get the answer right. What would you say? You might say 0, I'm sitting still. Or you might say, well, what is Muller getting at? Ooh, he told us earlier the Earth is going around the sun at 30 kilometers per second. So my velocity right now is 30 kilometers per second. Well, it's also true the Earth is spinning. You're going almost 24,000 miles in 24 hours. That's 1,000 miles an hour. So maybe you should put down 1,000 miles an hour. These are 3 different answers. Which one is right? The key thing is they're all right. All 3 answers are correct. You're not moving with respect to the seat reference frame. You are moving with respect to the sun. You're spinning around at 1,000 miles an hour with respect to the center. All 3 answers are right. The answer of what is your velocity depends on your frame of reference. Well, the same thing is true for length, for time, and for simultaneity. Now, those are things that normally, because the effect is so tiny, you don't expect there to be a big effect. In fact, the effect is quite small, which is why we teach our children to use their clocks. But in relativity theory, you lose simultaneity. this becomes very important for the philosophers. So let's not talk about simultaneous. Let's talk about bump, bump. Events where one comes before the other. Okay? Now, here's again my demo. Wish I could do this in the real world, I mean with real speed of light, but I can't. So here's my demo. I'm going to move my first hand, this hand down, and then this hand, right? Watch. Okay? I'll do it again. Okay? I'll do it again. Okay? I'll do it again. Right hand always comes first. Okay? Got that? What I'm telling you is that because of the funny behavior of time, this funny slowdown of time, that the order in which events take place is sometimes reversed when measured in a different frame of reference. The event that occurred first, measured in this lecture hall frame, with the axes and the clock that's fixed, if instead I measure with respect to my own ruler and my watch, I will find sometimes, I could write down the conditions under which this happens. I'll tell you about them in a moment. Write down the conditions under which this happens. Those events can be in the opposite order. It's called the loss of simultaneity. It has deep consequences for philosophy. And here's why. Suppose this event was not actually bringing my fist down, but was the pulling of a trigger. And this event was the, I don't know, the killing of somebody. Let me not say who. So, bang, dead. Suppose those are the two events. Now, this person is brought to trial. And they say, you killed him. He says, no, I didn't. What's your defense? He died before I pulled the trigger. How can I kill him if he died before I pulled the trigger? Now look, here's a frame of reference. All frames of reference are valid. I learned this in Physics 10. All frames of reference are valid. And now in this frame of reference, he died and then I pulled the trigger. How could I be responsible? Is that a valid defense? Getting into some interesting issues here about reality. Well, let me tell you the catch. If this event and this event, if the order can be reversed, then it turns out they have to be connected in a way that I'll explain. They have to be related to each other by something going faster than the speed of light. So, for example, if this person pulled the gun and a bullet came out that was going faster than the speed of light, that's the way the things work out. We'll do more of this next week. It's the way the numbers work out. If it's going faster than the speed of light, let's say, there's a name for that. It's called a tachyon. Do tachyons exist? Nobody has found any. Doesn't mean they don't exist. A tachyon is something, T-A-C-H-Y, on. It moves, the velocity is greater than c. Do they exist? Well, nobody's found one. Does that mean they don't exist? No, we are finding new things all the time. Are people looking for these things? Yes. You know, instant Nobel Prize, discover the first tachyon. How do you measure it? Not hard. You know, you're measuring the velocity. It's greater than c. It's easy. You just, but where do you find them? That's the trick. Let's go to some exotic places where certain energies and conditions are unlike any we've seen. Maybe that's what tachyons will be. If tachyons exist, could we make a gun out of them? Well, maybe. Make a gun out of it. Can you then use it to shoot somebody and then plead innocent? Because if you have a tachyon gun, if this event causes this one, but with an object that's traveling faster than the speed of light, if this event causes this event, if this pulling the trigger kills this person with a tachyon, then there will be a frame of reference in which they're reversed. If it's done with an ordinary bullet, then you can show that in all frames of reference, the order is the same. It's only if the two events are connected with a tachyon-like object that the order of events is different. I think you now understand why I'm not spending any time looking for tachyons. Because in my mind, I have no proof that tachyons don't exist, but they violate my concept of free will. If I could shoot someone with a tachyon gun, but there's a frame of reference in which they die before I pull the trigger, that doesn't violate anything in physics. It simply says the death caused me to pull the trigger. There's no physics principle this violates. A lot of physicists are absolutely comfortable with this. They don't believe in their own free will. They say that's an illusion. You think you have it, you don't really. And so the order of events is just an illusion. Things are invented, but causality can reverse. And if you don't think so, well, that's just because you got this hokey old religion where you think you have free will. And so I'm going to look for the tachyon gun, and I'll get my Nobel Prize, and you won't. Ha ha. Okay? My attitude is, I actually think I do have free will. And if that guy died, I could choose not to pull the trigger. And so I tend to think one of the following two things is true. Either tachyons don't exist, or there's no way we could use them in such a way. I mean, maybe we'll see them going by, but we won't be able to create them or stop them or anything like that. That they won't play any role in reality because of this loss of simultaneity.